Hello, Advanced Physics. This is Dr. Brenzi, and this is the video for lesson 7.3. And in this lesson, we're going to talk about a new type of acceleration called angular acceleration, and another type of acceleration that goes along with it, which is called tangential acceleration. And then we're going to actually be able to describe how torque and rotational inertia, which were the topics of our last two lessons, how those affect this new type of acceleration called angular acceleration. So in our last unit, we only ever talked about something that is going around a circle at a constant speed. But if you hop on a bicycle, you have to get it up to some constant speed by starting to spin these tires from rest. And you could imagine that they start off slowly, but then as you pedal and get up to speed, they spin faster and faster and faster and faster. Well, that process of changing the angular speed of the tire over time is what's called angular acceleration. So it can be either a spinning faster over time or a spinning slower over time. Either of those is angular acceleration. And so the formula for angular acceleration is delta omega, which is the change in angular speed over the change in time. And the variable that we use with angular acceleration is not the letter A. It looks like an A, but it is actually the Greek version of the letter A, which they call alpha. So we're going to use alpha for angular acceleration. Just like we use omega, which is another Greek letter for angular speed, and for angular displacement, we use a third Greek letter called theta. So there's a pattern going on here with all these Greek letters. The units of angular acceleration are radians per second, or radians per second squared. Now, closely related to the concept of angular acceleration is something called tangential acceleration. And tangential acceleration is the change in tangential speed over time. We give tangential acceleration this variable a, and then we put a subscript t next to it because we want to tell somebody that this is tangential acceleration. And that is the change in tangential speed over the change in time. And like any linear acceleration, its units are meters per second squared. Well, what's the relationship between these two new types of acceleration here? When we talked about, well, let me show you what's in the picture here first. So imagine something starting off on the outside of this circle and it starts at rest here. And then a second later, we take a snapshot of it and it ends up at this position. And then another second later, we take a snapshot, but it makes it a little farther, which means that the amount of distance it's covering every second is increasing. So we have some sort of acceleration. And another second later, we cover even more distance, so we are speeding up. Another second later, and finally another second later. So you can imagine what this looks like is it starts off really slow and then gets faster and faster and faster like that. Okay. So this thing is experiencing tangential acceleration. That is the change in its tangential velocity over time. Because you can imagine if I put a little vector for velocity, that vector is going to be very small here. And I'm not going to do every one of these, whoops. But you could imagine that over time, so maybe its velocity will get bigger here, and then it gets even bigger over here. Okay. So this tangential velocity is getting bigger and bigger with time. And that change in tangential velocity over time is tangential acceleration. Instead of thinking about distance that we're covering around the circumference of the circle, like we do with tangential displacement and tangential velocity and tangential acceleration, we can think of this angle that it changes instead. So you could imagine when this is starting up, after 1 second it covers a very small angle, and then after another second it covers more angle, even more angle, and yet still more angle. So its angular speed, the amount of angle it covers every second, is increasing. And that is the idea of angular acceleration. Now there's a relationship, just like there's a relationship between tangential displacement or arc length, which we called S, and we could go from S, from that arc length to that angle by multiplying by the radius of the circle, so S equals R times theta. We learned that tangential velocity is equal to the radius times omega, which is the angular speed. And then you can actually come up with a relationship between tangential acceleration and angular acceleration simply by multiplying the angular acceleration by the radius of the circle. Now, it's very easy to get this new type of acceleration mixed up with another type of acceleration we learned back in our last unit, which is centripetal acceleration. So let's compare and contrast tangential acceleration and centripetal acceleration. The two are not the same thing, okay? And we have to be very careful about the difference between the two. First of all, let's think about the properties of centripetal acceleration. The centripetal acceleration always points toward the center of the circle. So if we are at this point and we're traveling at this velocity v around the circle, our acceleration, centripetal acceleration, is pointing toward the center of the circle. And that centripetal acceleration is always present when you have circular motion. That centripetal acceleration is always going to be there. Even when we're going at a constant angular or tangential speed around the circle, so this would be uniform circular motion, so we're going at the same speed over and over and over again, we still have centripetal acceleration, which changes the direction of our velocity. If we have something spinning up or slowing down, that is when we start to have tangential acceleration. Notice in this picture over here on the left, there is no tangential acceleration. Okay, so when you are going at a constant speed around the circle, you do not have any tangential acceleration. The only time you have tangential acceleration is when you are speeding up or slowing down as you go around the circle, like over here on the right. So this depicts something that's going at a slow speed at first, but then speeding up as it goes around the circle. So it starts off slow and then it speeds up as it goes around. In this case, we do have tangential acceleration, and the direction of that tangential acceleration is tangent to the circle. So if we were to draw this tangential acceleration vector, we would draw it tangential to the circle. And since we're speeding up as we go around the circle, tangential acceleration has to point in the same direction as tangential velocity. If we were slowing down, on the other hand, then these two would be opposite. This would be pointing toward the right, and this would be pointing in the opposite direction if we were slowing down. So tangential acceleration points tangentially, and it's only present when we are speeding up around a circle or when we are slowing down as we go around a circle. Centripetal acceleration, on the other hand, always points toward the center of the circle, and it's always present even when we're keeping our speed constant going around the circle. Let's talk about Newton's second law now. Because we've talked about torque, we've talked about this thing called rotational inertia, and now we're talking about this thing called angular acceleration. And if something can speed up as it goes around a circle, well, is there something that is similar to Newton's second law that applies to circular motion? And the answer is yes. What we do is we replace the net force with net torque. We replace inertia, which is mass, with rotational inertia. And we replace linear acceleration with angular acceleration. So this is that alpha again. So what this is saying is that if I push on this with a net torque, if I have a lot of rotational inertia, I'm only going to get a small angular acceleration. Which makes sense because this I, rotational inertia, is an object's resistance to change in its motion. So if it has a large inertia, it should have a low change to its motion. In other words, a low angular acceleration. Let's actually show how we can use this rotational version of Newton's second law in an actual problem. So let's take this wheel. Same wheel. We're pushing on it with two different forces. One of them is 7.5 newtons, and we're pushing at the top of the wheel toward the right. It's kind of hard to see in this diagram, but let me draw that vector there. And then over here, we are actually pushing up, with a force of 5.3 newtons. And we're going to assume that this bicycle wheel is a mass of 1.5 kilograms and has a radius of 0.33 meters. We're asked two questions here. First of all, what is the tire's angular acceleration? And then B, we're asked what is the tangential acceleration of a spot on the rim of the tire. So let's tackle that first question, part A, and then we'll tackle part B. I need to get a little more space here, so let me clear all the information that we don't need. And let me make sure that we remember the mass of the wheel. Still have my arrows out there. M equals 1.5 kilograms. Okay. That information we also need to know. Okay, so we're going to use Newton's second law for rotational motion. So let's write that equation down. Tau net equals I times alpha. And in order to figure out the net torque, I have to figure out the torques that are acting on the wheel and then add them up together. So let's start off with this torque up here at the top. So that first torque is R, that's the distance away from the axis of rotation, which we were told is 0.33 meters. And then we have to multiply that times the perpendicular component of this force. Now this force is already perpendicular to the radius. If you're not convinced of that, let me draw a line representing the radius. So that force is already perpendicular to that radius. Oops, there we go. So that already forms a 90-degree angle, so all I need to do is multiply R times perpendicular force. So 0.33 meters times 7.5. And then if I evaluate that, I am going to get 2.48 Newton meters. Now, before I go on, I have to ask myself, okay, what's the sign of this torque? Because remember, counterclockwise torque is positive, clockwise torque is negative. And if I think about which direction this force is pushing the wheel, it wants to push in a clockwise direction. Oops. I wrote over my mass there. Let's see if I can fix that quickly. The answer is probably not, so let me just move this, erase that, and put it somewhere else. There we go. So that torque is clockwise, so I better have a negative sign in front of here. So I better make that negative 2.48 Newton meters. And let's put our let's put our mass up here. I think it'll be safe there. All right. Now let's evaluate this other torque over here. That guy right there. Again, it's equal to the radius where it's being applied times the perpendicular force. And if I drew a radius from here, from the pivot over to that where that force is being applied, those two would also form a 90-degree angle. That's a 90-degree angle, so I don't need to actually use the whole sine theta bit. So I'm just going to take 0.33 and multiply that times 5.3. And when I evaluate that, I get 1.75 Newton meters. And now I have to ask myself, which sign do I need to attach to this? This is going to push it in a counterclockwise direction. So that is going to be a positive torque. All right, so those are the two torques acting on the bicycle wheel. So I can just figure out what the net torque is by adding those two together. And I get a net torque of negative 0.73 Newton meters. Okay, so I figured out the net torque. Now I have to figure out what the rotational inertia of the wheel is. And the way I do that is I have to actually think about what shape this bicycle wheel resembles, and then I'm going to use the appropriate shape in my table of common moments of inertia. I'm going to ignore the spokes on the wheel. I'm going to assume that they contribute little to the rotational inertia. And so I think I'm just going to treat this like a hoop. And when I go to my table of rotational inertias and I look up a hoop, what it tells me is that the rotational inertia of a hoop is mr squared. So let's use mr squared. Let's plug in the mass of the tire, that's 1.5 kilograms, and then multiply it times the radius of the tire, which is 0.33 meters. We have to square that. And when I evaluate this, I get 0.163 kilogram meters squared. So that is the rotational inertia of the tire. Let me create a little box here, because now what I have to do is plug both of those things into this equation, and I get tau net equals I times alpha. Okay, we figured out our net torque is negative 0.73. And we figured out our rotational inertia is 0.163, so I plug those in. And then I solve for alpha, and I get alpha equals negative 4.5 radians per second squared. Now what does this negative sign mean here? Well, remember, negative sign when we're talking about angular motion is a clockwise direction. So this angular acceleration is actually pointing in the clockwise direction. So this tire will want to accelerate in a clockwise manner. All right. So that's the tire's angular acceleration. And let me quickly wrap up this video by answering part B. Let's go on to part B. What is the tangential acceleration of a spot on the rim of the tire? Well, in order to get that, what I have to do is simply multiply the angular acceleration times the radius of the tire. Let's plug in what we already know. We just figured this alpha out. That's the angular acceleration. Multiply it by the radius of the tire. And we get a tangential acceleration of negative 1.5 meters per second squared. Okay. That means that a spot on the tire is accelerating 1.5 meters per second squared in a clockwise direction. That's what that negative sign means. That negative sign means clockwise. It doesn't mean down. It means clockwise, because we're talking about circular motion here. So if we're on this spot of the tire, that tangential acceleration is actually pointing up. It's not pointing down. If we're over here, it's pointing to the right. And if we're right here, it's pointing down, and I think you get the picture from there. Because if I drew the next one, Ollie would think that I have some sort of crazy philosophy about life. And I don't want to be accused of that again. Anyway, so that's how you figure out tangential acceleration. And I look forward to seeing you tomorrow when we're going to actually get to put this to use and spin some tires up. All right, have a good evening and see you tomorrow. Bye.